Good morning.
Good morning.
All right, so it's 8 o'clock. We'll get started here. Just to let you know where we're at. So we've got Tuesday, next Thursday, the test will be due. The test 3 will be due next Thursday. So I'm going to, well, I don't know if I'll end up completing everything today, but it's going to go close. Probably end up doing a couple of examples of what we're doing today on Thursday as well. But then that gives me time to go back and take a look at some of the stuff that you might want to go over that I didn't teach during that first week after spring break, but it gives me a chance to do that if that's something that anybody had trouble with at the time. All right, so let's go back to where we were at. We'd finished up with the redox equations. Let's continue with electrochemical stoichiometry and see where we're at with that. Now, this is just by way of kind of an introduction to an application of cell potentials to single displacement reactions. Now, this is not directly relevant to any test problem, but it does have some relevance, especially to the direction of flow problems that we'll look at in a little bit. But I think it's worth going through this just to give you a little bit more context for how we determine if a single displacement reaction is going to occur or not. When we go back to single displacement reactions, it's something you would have covered back in Intro to Chem and General Chemistry 1, I'm sure. These are reactions where we have a solid and something aqueous, and then that solid turns into something aqueous, and the something aqueous turns into something solid. And these are actually a redox process. So it starts that something gets oxidized and something ends up being reduced. So you can see here the A ends up being oxidized because the electrons are on the product side, and the Bx plus ends up being reduced because the electrons are on the reactant side. So what we can say here is if the spontaneous reaction is indicated by positive E naught, then if the E naught cell is positive, then we can determine if a single displacement reaction is actually going to go or not. So excuse me. So an example might be something like this, where we've got zinc plus Fe2 plus. So the zinc, if we look on the, let's go to the tables here. Now remember, these tables are provided to you in the test 3 folder. It's this one here. And the reduction potentials that we're talking about are sort of more towards the end of this document. So we've got zinc. Now we know the zinc is going to become something positive. There's actually only one reaction here where the zinc turns into anything. And where is it? Is this one here. So zinc 2 plus goes to zinc. So that's the reduction potential. I'll do this from sort of scratch here so you can see. Oops, I didn't want to do that. I did not want to do that. Close that down. There it is. So zinc 2 plus 2 electrons. This is the only thing that involves zinc at all. Something's slowing me down here. I'm not sure what it is exactly. Okay, that's better. And that's negative 0.763 volts. And the other one is Fe2 plus, and you can see that one here. And that is negative 0.440 volts. Now the thing is, the reaction involves Fe2 plus zinc. So we know that we have to flip that top one. So that becomes zinc gives zinc 2 plus 2 electrons. And that would be positive 0.763 volts. And the other one remains the same.
I have a question.
Yes, yeah.
Why did you flip zinc again?
Because the actual, if we look at the actual problem, it's zinc plus Fe2 plus, right? And the zinc is on the wrong side here. See, it's on the product side.
Oh, okay.
So that's why I had to flip it.
Okay, thank you.
But remember, with all these processes, something has to get flipped, right?
Yeah.
Anyway, that's and you can see the math here on the slide. We end up getting a positive E0 cell, which tells us that if I add Fe2 plus to zinc solid, I should get a reaction. That's the whole point of it. So if we take the reverse case here, another case where we've got silver, and you can see with silver, there's a reaction that involves silver plus an electron. It's positive 0.800 volts. And I flip that around, just like I did the zinc over here, it becomes negative 0.800. The point is that if I took Fe2 plus and added it to silver metal, I expect not to get a reaction because the E0 cell is negative. So that's really the only point that I want to kind of make here. And this is going to be used a little bit later when we're talking about direction of flow problems, especially applying the fact that positive E0 cell values are the ones that indicate that a reaction is actually going to go. So that's really the entire point of what I'm trying to get at here. Does anybody have any other questions? Okay. So a lot of you may be aware of the concept of electroplating, and that is the process by which we take a metal and then we plate another metal on that metal using electrochemical means. So in this instance, I've got a picture of a spoon, which is iron, or stainless steel or something. And then we've got a silver metal bar attached to that spoon via a battery. And what can happen is we can put electrons into the spoon, and the silver will turn into silver plus, and that silver plus will turn back into silver as it coats the spoon. And that is going to happen because, well, it's not a spontaneous process, but if we put a battery in and allow the supply of electrons to occur, then we can make this happen. The kind of application problem that we can make from this is something like this. How many grams of silver will be deposited on a cathode? Because that's what the spoon is. The spoon ends up being the cathode here. In 1 hour, 1.00 hours, by by a current of 1.50 amps. All right, so in order to do this problem successfully, we need a little bit more information about how to convert time and amps into coulombs, which can then be converted into grams essentially by using this reaction here. So it looks complicated, it actually isn't that bad. But what we know is this, is that charge, which is going to be given the, sorry, looks like my computer's slowing down again here for some reason. So if you've got Q in charge in coulombs, is actually going to be current, which is in amps, multiplied by time, which is in seconds. And amps is actually also coulombs per second. So what are coulombs? Coulomb is a measure of charge, electronic charge specifically. And this is relevant because we actually have something that is a constant, that's the Faraday constant, which tells us that 1 mole of electrons carries 96485 coulombs of charge. So that's the end game here, or what allows us to get to moles of electrons, which then can get us to moles of solid, which can also get us to grams of solid eventually. So the first step here is to figure out the charge in coulombs, and we can do that by taking 1.50 amps, which is coulombs per second, multiply it by the time, which is going to be 1.00 hours, convert that into seconds, 3,600 seconds per hour. That's 60 minutes times 60 seconds is 3,600. Now, if I stop right here, what I'll be left with is coulombs. But I want to convert that into moles of electrons. So I can do that by multiplying by the Faraday constant. This is something you'll be given, by the way. You'll see this on the test. It's not something I hide from you. So it's 96485 coulombs per second. Now you can see that, no, I'm in the wrong. Sorry about that. 1 mole of electrons, I meant to say, is 96485 coulombs. And you can see that if we did that, we could cancel out everything, the hours, the seconds, and we're just left with moles of electrons. We do have a relationship here, a stoichiometric relationship, that tells us that 1 mole of electrons produces 1 mole of silver solid. So that's the next step. 1 mole of Ag over 1 mole of electrons. Let me close down Word here. I wonder if that will help speed things along here a bit. Okay. And then to get to grams, it would be 107.87. That's the molecular weight of silver. We can get that off the periodic table. And that is how much 1 mole of silver weighs. So by doing that kind of dimensional analysis, we come up with the figure that's 6.03 grams. That's how much silver we could actually deposit on a cathode. All right, does anybody have any questions? Anybody have any questions about this? Let's take a look at some resources I have for this. and it's in the stoichiometric electrochemistry problem folder. I do have some examples here, or at least some problems with answers. I just want to go through one of these and then of course go through the problem, and you'll see on the test as well that relates to it. It's actually not incredibly difficult. You'll see that in a second. Okay, so let's look at one that involves more than one electron. We'll look at the second one here, the lead. So the idea here, again, we've got the current, which is 1.50 coulombs per second, multiplied by the time, which is 3.00 hours. And that needs to be converted into seconds, so 3,600 seconds per hour. And then that would give us the coulombs. So we need moles of electrons. As I said, this is something that's provided to you, this relationship. You don't have to remember it. And 1 mole of electrons is 96485 coulombs. Now, according to what we've got up here, 4 moles of electrons gives 1 mole of solid. So 4 moles of electrons goes on the bottom. 1 mole of Pb solid goes on top. And then the last step here, I'm just trying to remember the atomic mass of lead. I think it's... Can anybody tell me? I don't have a periodic table in front of me. Has anybody got a periodic table? I can't remember the lead off the top of my head. 200 point something? Yeah, 207.2. Thank you. That sounds right. 207.2. Thank you. Grams per 1 mole of lead. Anyway, once you've done all that, it comes out to be 8.70 grams of Pb. So it all depends. For these kinds of processes, you're always given a reaction as well as a time and a current, plus the relationship here, which is all important, the 1 mole of electrons from 96485 coulombs of charge. So I do have those examples there that you can do as well. They're in
I have a question.
Yes.
Why did you times it by the mass of Pb in this equation, but not in the last equation?
Well, in the last equation, I did the mass of silver.
Oh, okay.
Which was also off the periodic table. So it all depends on what element you're using, Alexandra.
Okay.
Is that okay?
Yeah.
Okay. Let's take a look at the problem. The problem on the test is not really that bad. You'll see in a second. I also want to go through the essay question, which I'll do in a second. Somebody had asked me about that and was concerned about it. Just want to make sure. Who was it? Who emailed me about it? I can't remember who it was. Somebody did. They wanted me to look at it. Oh, it's Kate. That's right. Yeah. But I'll go over that in a second. Okay. Let me show you this on the ungraded copy, and then I'll go through the essay question. Okay, let's see. Gibbs free energy, nature delta G, non-standard cells, electrochemical stoichiometry. Here we go. So as you can see, I've got the Faraday constant here in the question, 96485 coulombs per mole. So you don't have to remember that. And then I give you this thing here where we've got how many grams of X, and I give you in grams, and I'll give you the molecular weight of X, it will be deposited on a cathode in 1.74 hours by a current of 2.60 amps. I'll go ahead and I'll at least do the work on it. As you can see, it's going to follow that same kind of pattern. It's all about dimensional analysis though, just seeing what cancels where. So if we start off with 2.60 coulombs per second, multiplied by 1.74 hours, which gets converted into seconds, and we're left with coulombs. And we know the relationship is 1 mole of electrons over 96485 coulombs. Again, we have that up here in the problem. And then we can see that we need 5 moles of electrons to get 1 mole of X solid. And then we can multiply that by the molecular weight, 40.47 grams of X over 1 mole of X. And that gives us our final answer. Does anybody have any questions about electrochemical stoichiometry? I don't think it's that bad, really. All right. Let's, actually, I'll leave that open. No, I won't. I'll close it up. We'll come back to it later. All right, let's talk about this essay question, and I'll see if anybody has any other questions about it. As I said, I've got one inquiry about it. I just want to make sure everybody understands what they need to do. So there is an essay question you're going to have to hand in. It is worth 20% of the test, but it's actually not that difficult to do. And I do provide for you an actual example of what I'm looking for. Now, all of these topics, we're not going to discuss in class. You're expected to do the research yourself on these. There's plenty of stuff everywhere about them, though. In your textbook, it should just be a matter of looking in your, I know, oh, hang on. Let me make my connection here more stable. I didn't even have my Ethernet in here. There we go. That should be better. All right. Hopefully that'll speed things along with the internet. So these are the topics, and all of them here are redox problems. They're all redox based topics. You are expected to write 50 words about each of these topics and to provide a reaction that relates to what you're writing about in the essay. Now, there's a certain, you can find the stuff in your textbook or on the internet. There's plenty of information about all of these. And before the test, well, which means effectively before test 3 stops being available, you need to hand in the essays, and they must be handwritten, not from a Word document, not photocopied. It'll be 20 points. All the essays must be completed. Be sure to include a household object I specify in the Dropbox. And that household object is going to be a teaspoon that needs to be included with each picture, a real teaspoon, not just a photoshopped copy of a teaspoon or anything. A real teaspoon needs to be actually on the document when you're taking pictures of it. Okay, what was your question? What's unclear?
I was mostly confused about the teaspoon part. Like, do you want us to actually do the reactions and then, like?
I want you to put it like this picture. See this? Do you see this picture here?
Yes.
You would lay a teaspoon on the page.
Okay.
The reason is so that next semester somebody can't take the document, that they did this semester, give it to another student and just have them hand that in. That's the whole point. I mean, I'm going to require a different object next semester.
That makes sense. For some reason, I thought you wanted us to like do the reactions and then have a teaspoon with whatever the reaction.
No. The teaspoon is it's an anti-cheating mechanism. That's all it is.
Okay.
To be completely blunt, that's all it is.
And my other question was not really a question, but more of just a clarifying statement. These are all in our textbook, right?
Well, yes, you should be able to find information in your textbook. If you can't find information in your textbook, then you can look online. But many words have been written about all of these, and you shouldn't have any problems finding information about any of these topics. My recommendation would be to get them done earlier rather than later. A lot of people, what they tend to do is, of course, when do they do it? They do it the day it's due, right? That leads to, shall we say, a little bit more stress because people are trying to get the test done, and then they're saying, oh no, now I've got to do these essays as well. And it's just too much stuff to do on one day, especially if you've left doing the studying for the test till the day it's due as well. It's just too stressful. I just don't know why people would do it. Get it done early. You can, and don't look upon it as being something that is not of benefit to you. I mean, if this is worth 20%, and if you do it, if you do what I ask you to do, that's a full 20% that you get. I mean, that goes directly towards your test score. I mean, I don't know. I think it's a benefit rather than a curse. That's the way I see it. How long should it take you? Well, I don't know. Probably about an hour, I imagine, to do it. I don't think it would take that much longer than that. If it's taking 3 hours, you're spending too long, I can tell you that. Between 1 and 2 hours, I'd say it should take you to do it. It's not hard to find the information. Does anybody have any questions about the essays? So there's a Dropbox somewhere, and it's in the test 3 folder. That's where
I
you
have a
put it.
question.
Yeah.
So do you want us to like cite our sources or anything
No.
like that?
No,
Okay.
Alexandra, no. I'm not even looking for that. No, you see, that makes it even quicker to do because you don't have to cite your sources. That's why I'm saying, you're looking at these. There's how many topics? 7. They should take no more than 10 minutes each to find the information, get a reaction, write 50 words. 50 words isn't much. It really isn't. And I've got some examples here too. See? All right. Does anybody have any questions?
When you say no photocopy, do we scan it and send it to you, or?
Yeah, that's right. It goes in the Dropbox. Okay. Yeah, because you'll handwrite it and then take a picture of it with a teaspoon on it, and sign across it too, Alexis. You see it like this person's done? Does anybody have any other questions? All right, so you're all clear on this? Okay. Let me see, is there a units quiz here too? I think there might be. Hang on. Let's go back to where I was. Okay, that's the next. That's not going to get me where I need to be. Let's go back to where I was. Okay, is there a units quiz too? I'm just trying to determine that. Yes, here we go. Now, a lot of these, obviously, you can't show your work on them. So I have a units quiz that's also part of the test too. I think it's you have unlimited attempts on it. Yeah, you do. And this is the kind of question that you're going to have to do. It's a matching type thing where you have to put the units in each place. So it's my way of getting you to make sure you understand the dimensional analysis. And you see for this problem here, the one we just did, you can see the setup there as well.
Is that proctored as well or no?
No, it actually isn't. Now, I'm not going to take that question negatively, but yes, it isn't proctored. Which makes it relatively easy, really, I think, because you can have the stuff in front of you, I guess. Nobody's going to say anything about it. All right, that shouldn't be that big a deal, but yes, that's also part of it too. Okay. All right, does anybody have any other questions that they want to ask? I don't want to do that. Any other questions? Okay. So Cade, you're completely clear on this now?
Yes.
Okay, good. All right. Okay, let's take a look at this next thing here. This is the last topic. I actually think these are kind of fun, but I don't know, not everybody agrees with me on that. Okay, this is what I'm calling a direction of flow problem. And what we've got here is an electrochemical cell. And there's a substance W, which is copper metal. So that's a metal block in there, in a solution of X. So the X is pointing into the whole beaker here, which is a solution, which is copper nitrate. So as I had talked about last time, there's a difference between copper and copper 2+. Copper is a solid metal that's copper colored. Copper 2+ is a blue liquid. So this would be copper 2+ in this blue liquid here, which is X. Then you've got lead, which is the Z over here, this other block, which is in a solution of lead nitrate, which is Pb2+. So you have copper in copper 2+ and Pb in Pb2+. So those are the things that are interacting. Through this wire, we have electrons flowing. And then through the salt bridge, we have ions, negative ions flowing as well in order to make this go. And then we've got a bunch of letters here that will state the direction of flow of different species in the actual electrochemical cell. Does anybody have any questions so far? So looking at what it says, this is really the most important thing. Assume the cell is working spontaneously and is working under standard conditions. Working spontaneously means that that's going to define which reaction it's going. And the other thing it says is it may or may not obey the conventions of a standard cell diagram. What I mean by that is when we set up a cell diagram, we automatically make the first thing the anode. The thing on the left is the anode. But in this kind of diagram, the anode could be on the left or the right. And you'll have to decide which one is the anode and the cathode by determining which produces an E0 cell that's positive. Just as we were talking about earlier with the single displacement reaction. Spontaneous reactions are only going to result if we have a positive E0 cell. So depending on the direction, it's going to be positive or negative. So let's take a look at how we determine that. These are all the things you'll be required to identify. Electron flow, direction flow of nitrate, copper 2+, lead 2+, species being oxidized and reducing agent, oxidizing agent, anode and cathode. So those are all the things you're going to have to identify off this diagram. They're all going to correspond to one of those letters. So here's how we handle the answer on this one. When you go hunt these down on the table, we've got two systems that we're interested in. We've got copper and copper 2+, and we've got lead and lead 2+. All right, so where am I getting that from? Back up here, these are the conditions you'll be given. You've got copper, and then you've got copper and then nitrate. Nitrate has a -1 charge, so this must be copper 2+ that we're dealing with. And this again must be lead 2+, and that must be lead. Does anybody have any questions so far? So I can go hunt these down on the table. I can see the lead somewhere, I hope. Where's the lead? This isn't it. This is something else. This is PbSO4. We need something involving Pb2+. There it is there. So Pb2+ plus 2 electrons gives Pb, and that's -0.125 volts. And then we've got the copper 2+, which is up here. So I just had to find the equations that were relevant to that. That's +0.340 volts. All right, so here's the story at this point, and I'm going to show you this summarized on the next page here. There are two possibilities that we can entertain here. We know that one of these needs to be flipped. We know that one of them needs to be the anode and one needs to be the cathode, which means whichever one gets flipped, that one is going to be the anode, the one that is going to be the oxidation process. So these are both reductions as they appear on the table. One of them needs to be turned into an oxidation. The question is which one? So looking at the first example, you can see if I make the copper the anode, that is, I flip the copper, and you can see that's what I've done. That's what I've done over here. Do you see that? That one's been flipped. And that would lead to a E0 cell that is negative. However, if I take the lead and I flip that, that becomes +0.125 volts. And when I add them together, I get a positive E0 cell. So the second one is the one that is correct. Does anybody have any questions? Anybody have any questions at this point? Okay. So what I can do is I can label these with some things that are going to be helpful to me. The first thing is that if in the copper reaction, this is a reduction. How do I know it's a reduction? Because I didn't flip it and the electrons are on the reactant side, so it's a reduction. Reduction occurs at the cathode. And the other thing I can say is that it's plating. Now, what do I mean by that? I'll take you back up to this example of a cell diagram that I gave you a while ago. And there it is here. And if you you'll remember what happens here. One side has an electrode that's dissolving. The zinc is turning into zinc 2+. And here the copper 2+ is turning into copper. It's actually making that metal thicker. It's actually plating. So we're actually plating that electrode. And that'll always occur on the cathode side where the reduction is occurring. So likewise over here with the lead, you can see the lead is turning into lead 2+. So that's an oxidation. And that is the anode. And it's dissolving. Does anybody have any questions so far? All right. So the main thing here is for me just to explain what's happening during the process and to figure out how to get these letters assigned correctly. Okay. So here's what you have to do. Identify each of these. And you see I've already got the letters here, but I'm going to go through and explain exactly how I get those. Now, the direction of electron flow. Now, electrons are flowing through the wire that joins the two electrodes together. So the answer for A here can only be A or B. Big A or big B. So which direction is it? Well, looking at the reaction, you can see which way the electrons are flowing. The lead is producing lead 2+ plus 2 electrons, and the copper 2+ is accepting 2 electrons. So the electrons are flowing from the lead side, so from the lead side over to the copper side. And that would mean that direction is A, going from the lead to the copper. All right, I'll stop there for a second. Does anybody have any questions?
Yeah, I have a question.
Mm-hmm.
So, you picked W for the copper and Z for the lead.
Oh, no, that was already assigned. Back up over here.
Oh, okay, never mind.
Now, yeah, I didn't have to come up with that. That was already given.
Okay.
All right. Does that help?
Yeah.
Okay. All right, let's do a little poll here. That's what I'll do, I think. Yeah, don't worry about the I was not here Tuesday option. So we're just talking about the electrons here. How do you feel about the electrons? 5, 4, 3, 2, 1. I haven't got very many people here today, but only 8 people have voted. So I don't know if those other 3 people who aren't voting don't want to vote. Come on, everybody vote. All right, you don't want to vote, that's fine. All right. Anybody have any questions that they could ask about the electrons here?
I have a question.
Uh-huh.
So the direction of the electron flow is to the copper. Is that because the electrons are on the reaction side?
Yeah, that's one way of looking at it. The other thing, if you look at the lead, see how it's on the product side? So the lead is giving the electrons away.
Oh, okay.
And the copper 2+ is accepting them.
Okay.
I think that's the best way of looking at it. All right. Any other questions? All right, let's look at the flow of nitrate then. So the nitrate is going to flow through the salt bridge. So it's either going to be C or D. Now, if you look at what's going on here, the copper 2+ is turning into copper. Now, the copper 2+ does have nitrates associated with it. Because it's 2+, it must have NO3 minuses, 2 NO3 minuses with it. And when it turns into copper, copper solid, it doesn't need those nitrates anymore because the copper is neutral. However, on the other hand, the lead is turning into lead 2+. The lead doesn't need nitrates, but the lead 2+ does. So the nitrates are going to flow from the copper side over to the lead side, which means they're going to flow this direction, which is going to be D. But spoiler alert here, the nitrates are always going to flow in the opposite direction to the electrons. And the reason for that is because nitrates are negative, electrons are negative as well. They can't be flowing in the same direction. How do you feel about the flow of nitrate? Come on. I'm not going to give you too long to vote on this, actually. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Still only getting 9 or 10 people to vote. Anybody got any questions? Okay. Direction of flow of copper 2 plus. Now, as I said earlier, the copper 2 plus is plating. So the copper's over here, it's plating. It's turning into copper solid. So the direction here is either going to be E or F, but it's going to be E because the copper 2 plus is going to be flowing towards the copper electrode so it can plate on it. Copper 2 plus is turning into copper. Direction is E. Does anybody have any questions?
I have a question.
Yeah.
So the copper 2 plus is plating because it's a reduction reaction, right?
That's right. Mm-hmm.
Okay.
Yeah. All right. So how do you feel about the copper 2 plus? Five, 4, 3, 2, 1. I'm only ever getting 9 people to vote here. I don't know what the other 3 are doing. I wonder if they even have their video on. Good. Everybody does. That's good. But I don't know. I guess it's like the US. You don't have to vote, I suppose. All right. Any questions? Any questions about copper 2 plus? All right. What about lead 2 plus? Direction of flow of lead. As I said, the lead is dissolving. So the PB is turning into PB2 plus. It's going to be over here. This is where the lead is. And that means that it's turning into lead 2 plus, which makes it H. Dissolving. How do you feel about that one? Five, 4, 3, 2, 1. Okay, I do have a don't understand at all. All right. Any questions? I mean, that's a pretty stark statement there. So, any questions? I mean, come on, if you don't understand at all, you must have a question to ask. Seriously. Any questions? Any questions? Somebody here doesn't understand at all. That disturbs me a bit. I just want to see if I can rectify the situation at all or not. Okay. All right, when we talk about species being reduced, then it's important to note which is an oxidation, which is a reduction. Now, the species being reduced is the copper 2 plus. A good way to tell if something is being reduced or not is to look at what's happening to the charge. In the case of copper 2 plus, it's going down. The charge is going from 2 plus down to 0. And if you look at the lead, it's going from 0 up to 2 plus. That's an oxidation. Even the word reduction tells you what's going on with the charge. It's going down, it's being reduced. That's the whole point. That's what reduction means. It means the charge is going down. Copper 2 plus is turning into copper 0. In the oxidation case, it's turning from lead 0 into lead 2 plus. So the species being reduced is the copper 2 plus, X, not the W, it's the X. The 2 plus, the copper 2 plus is being reduced into copper. Anybody got any questions? Species being oxidized, that's a lead turning into lead 2 plus. So the species being oxidized is the Pb, the lead, which is going to be Z over here. Yeah. Does anybody have any questions? All right. Things being oxidized and reduced. Let's see where you're at with that. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Any questions? Any questions to help out here? Okay. All right. These two here, reducing agent, oxidizing agent, they're the hardest ones to understand, I think. So when I use the term agent, the word agent itself means cause of, something that causes that. So the species being reduced is Cu2 plus, but it's not the reducing agent. I mean, it doesn't cause itself to be reduced. Something is actually causing it to be reduced. So what is causing it to be reduced? Well, you see the reduction is occurring because the copper 2 plus is accepting electrons. Where are those electrons coming from? Well, they're coming from the lead. So the Pb is actually the reducing agent. Likewise, the species being oxidized is the lead. Why is it being oxidized? It's being oxidized because it's giving up electrons. It's giving up electrons because the copper 2 plus is accepting them. And the copper 2 plus then becomes the oxidizing agent. But the bottom line here is that for the species being reduced, it will always be the oxidizing agent, and the reducing agent will always be the species being oxidized. So just remember that whatever's being reduced can't be the reducing agent. It has to be whatever's being oxidized. I mean, something doesn't cause itself. The copper 2 plus doesn't do it spontaneously. It does it, it reduces because it's accepting 2 electrons, and those electrons are coming from the lead. So whatever's being oxidized is the reducing agent. Now that is fairly complicated, so this will be interesting to see how you feel about reducing and oxidizing agents. Let me try it again. I don't think I got that. Let's try it again. Let's see. All right. Reducing an oxidizing agent, how do you feel about it? Five, 4, 3, 2, 1. Yeah, I'm actually kind of surprised. I'm a little bit surprised. I expected a lot more people not to understand that because that is complicated. All right. Does anybody have any questions then about reducing and oxidizing agents? All right, the other two are fairly easy. These are the anode and the cathode. Now, these are electrodes. Electrodes are bits of metal stuck in the solution. And as I had talked about earlier, back over here, oxidation occurs at the anode, reduction occurs at the cathode. O and A are vowels, R and C are consonants. So I had gone through that a bit earlier. So the reduction is the electrode, that's the copper, that's the solid, the bits of metal stuck in the solution. So the anode is the lead, because that's where the oxidation is occurring, and the cathode is the copper metal here, which is W, and that's going to be the cathode, where the reduction's occurring. Does anybody have any questions about the anode and cathode? All right. How do you feel about the anode and cathode? How do you feel about the anode and cathode? Yeah, I could be wrong, but I suspect that there's always been one person who understands it halfway. I suspect it's the same person on all of these, but I'm not 100% sure. All right, there's a number of people here who are not quite getting the anode and cathode, so I'm expecting questions here. 3 of you understand it halfway, so tell me, what can I do to help you with the anode and cathode? Any questions? This thing on. Any questions about anode and cathode? I can't help you if you don't ask a question. All right. So I can give you some tips about this, and this is probably useful to realize, just so you can refer back to this. The electron flow is always towards the plating electrode. So as we saw earlier, whatever's accepting the electrons is always plating. So that's what we can always say. Nitrate flow is always towards the cell forming the cation. So you can see lead is turning into lead 2+. That needs the nitrates. But it's also the opposite to the electron flow as well. Cation flow. Cations flow towards the plating electrode and away from the dissolving electrode. We talked about that. Species being reduced, the reactant involved in the reduction, the reactant involved in the oxidation is the species being oxidized. Reducing agent, the reactant causing reduction. Oxidizing agent, the reactant causing oxidation. And the anode and cathode electrodes at which oxidation occurs, and cathode electrode at which reduction occurs. So those are the little tips that I can give you to help out with each of those. All right, let's take a look at some of the fun we can have with these. And it's under galvanic cells. I do have a cool problem solving document here. And it's this one here. It's in the galvanic cells. It's in the galvanic cells folder. And you'll be required here to look at the diagram. You're given W, X, Y, and Z down here. And then you are asked to figure out each of these things that we were just figuring out before. And if you look at the answers, you'll see that they're not all the same. And that's because, but you will notice that they do kind of follow a pattern here. And that all depends on what the anode and the cathode is. So in one case, the anode is W and the cathode is Z. In the other case, the cathode is W and the anode is Z. So it could be either way here, and that's going to determine what you're getting in each of these instances as the answers. But my recommendation would be to do the examples here using the tables here to get the reactions you need. So I'll look at the first one here, for example. Titanium and nickel, so the reactions would be Ti2+ to titanium, that's 1. And then you've got the nickel to nickel 2+ up here. So you use that to make your determination as to how the reaction's going to go, and then you go from there. But obviously getting that right in the first step is really going to be the key factor. Does anybody have any questions? All right, so that's that resource. There is also this fun quiz which I think is well worth doing. A lot of people don't like it initially, but after they understand it, they don't mind it so much. I'm going to go through one of these so that you can see exactly how to do it. So what I do, it's the same kind of setup as we had before, except now it's not W, X, Y, and Z. It's I, J, K, and L. That's just so that the letters come out to be alphabetical, which is kind of cool. And I've got these fictitious elements here, Q and R. Q and Q plus, which is effectively what QnO3 is, and R plus is RnO3, and then you've got R, which is R solid. So, sometimes people look at this and they don't know how to deal with it, but here's the thing. If we're talking about reduction potentials, then what we're looking at here is Q plus an electron giving Q. And the reduction potential would be 0.923 volts for that. Now this is a reduction because the electrons are on the reactant side. The other reaction is this. It is 0.459 volts. So your first decision here has to be, well, which one do I flip? Let's do a little poll and see how we go. Hopefully I won't be asked to sign in again here. That's good. All right. All right. Okay. So what do you think? Which one is the oxidation? Is it the first reaction or the second reaction? In other words, which one do you flip? They're both reductions right now. Which one becomes the oxidation? Let's see. I'll give you 5 more seconds. 4, 3, 2, 1. Okay. Looks like everybody's up. And there we go. We have a 50-50 here. The second one is the answer. A second one. All right, let's see how that works. So if you look at it, if we were to flip this, then this becomes negative 0.459. So it would be 0.923, which would stay the same. And the other one becomes negative 0.459 if we flip it around. So when you add these together, it comes out to be a positive value. Can anybody tell me a good rule that you could apply here to knowing which one to flip?
The smaller one.
The smaller one. Congratulations. Yes, I like that. The smaller of the two. So whichever one's the smaller of the two, that's the one you flip. I hope that clears things up for people. Does anybody have any questions? Does anybody have any questions? All right. Okay, now the catch with this specific exercise is that they change each time. So whatever's the anode and the cathode is going to change around because these reduction potentials change. So let's look at this next one here, and we'll see. I think this one, this time I'll get a better result. At least I'm hoping for it. Okay, let's see. Let me move this up here. Okay, so the Q is 1.235. And the other one is negative, well, actually positive. It's going to be positive 0.459. No, negative 0.459 is right. Yeah, okay. Okay. All right. Which one gets flipped? Which one gets flipped? I'll give you another 5 seconds. 5, 4, 3, 2, 1. Make your best guess. Okay. All right. Second is the answer, and I got a much better result this time. It's good. Anybody got any questions?
I have
Remember
a question.
Yes,
But
Alexandra.
like not about this one.
Okay, I'll get your question in a second. Okay.
Okay.
So for this one, if you flip this one, it becomes positive. So adding these together will definitely give a positive number. But as you can see, out of these two, the smaller one is definitely the negative 0.459 and 1.235. All right, Alexandra, what was your question?
So, I just want to make sure that I'm understanding like what is reduced and which one is oxidized.
Mm-hmm.
So, since the R equation is really an oxidation equation.
It isn't right now.
Yeah,
Yeah, but when it gets turned around, it is. So, you know, that becomes, so the Q1 stays the same and the R1 turns into an oxidation. That's right.
So with the whole like what is reduced and which is oxidized, the reduced, would that be the Q plus?
Yes.
And the oxidized be just the R?
That's right.
Okay. I just wanted to clarify that.
That's good. That's all right. Yeah. They're always reactants, Alexandra. You know, they're always on this side of the arrow. All right. Just look on that side of the arrow to figure out what's oxidized or reduced.
Thank you.
Okay. Does anybody have any other questions? Anybody have any other questions? Okay. All right. That's definitely fun to do. I think it's well worthwhile. Because if you can do that, then you can do anything. A lot of people try and leave that to the last day to do, obviously. It's just still a mystery I'm trying to solve, why people leave things to the last day, but you know, it's a mystery I don't think I'll ever solve. It just doesn't square with me. I cannot fathom why people would wait until the last minute to do anything, but anyways, it is what it is. What are we looking at? Let's look at the test here. I don't know. I don't feel like a lot of this stuff is really that difficult for test 3. I don't think it's that bad.
I have a question.
Yeah.
So for Thursday class and Tuesday class, are you just going to go over what we missed in the 2 classes that we didn't have?
Well, and review the test too.
Oh yeah.
Yeah. But a lot of it, Alexandra, will be me doing what you just said, but in the context of what's on the test, more than actually giving full lessons about the stuff, more just applying it to the test. because I'm going to
Okay.
assume that you've at least looked at it.
Yeah.
All right. And then we can see how it exactly applies to the test. And that's going to be my main focus. I think it's going to be worth definitely attending on Thursday.
Okay.
It may not be worth your while to attend next Tuesday. No, possibly. Depends. It depends on how much help you need.
Okay. Thank you.
All right. So question 10 is the one that relates to the test here, and you can see it's a matching problem, and it's set up pretty much the same way as the previous one was, except that now it's all matching here. That doesn't make it any more difficult, really. This is all going to be the same order. What's going to change is the order of these guys down here, so that won't be a constant thing. But it's just, but you're being asked the same kinds of questions, and you'll set this up exactly the same way as we set up what we just did. All right, so looking at this one, let's see if you can figure it out. Where's my pulse? Here we go. Okay. When I say top and bottom, or first and second, so which one gets flipped? I guess is the question here. First or the second one, Q or R, Q being the first, R being the second. Which one gets flipped? I'll give you 5, 4, 3, 2, 1, 0. Okay, so which one gets flipped? The people who said second, you got it right. The people who said first, you got it wrong. No poll came up for you, Kate. I'm sorry. Maybe you just didn't see it. I'm not sure. All right. So how do we know this? Well, look at the two. You have minus 0.4 and you got minus 0.5. Which one is smaller? Minus 0.5 is smaller than minus 0.4. See, when you flip this around, it becomes positive 0.5. Minus 0.4 plus 0.5 is positive 0.1. So it's the second one that gets flipped, not the first one. Does anybody have any questions? Any questions? A lot of you got that wrong, so I want to make sure you understand it. It's always the smaller of the two, numerically the smaller of the two. I think some of you got mixed up with bigger and smaller. All right. Any questions? Okay, well, we'll leave it there for today. On Thursday, I'll give a brief introduction to the stuff that we went over, or didn't go over, I should say, or the stuff I didn't teach actually as a Zoom session. But remember, I did put up Zoom sessions for it. All right, they were old ones, but they're still relevant. They still do the same thing as pretty much I was going to do on Thursday, sorry. And then I'll show you exactly how that applies to the test as well. All right, that'll be my main focus on Tuesday, and then I'll do a little bit more review of some other things if I have time. And then on the following Tuesday, it's just going to be pretty much straight review, any questions you might have. But, there's plenty of time here, and I really believe that this test is not that hard, and I think you should take advantage of it and try and do the best you can. And that really, the secret is just starting early and not waiting to the day it's due to do it. If you do that, I think you'll be okay. That way you can also seek help too if you need it. Okay. All right, we'll leave it there for today, and I will talk to you later on. Thank you. Bye. Have a good day.